Hello everyone. Today's problem is a graph problem. We are given a 2D array which forms a matrix. You can think of this array as pixelated art. So each color can be represented by a grid of numbers. We have to implement the flood fill function. How does the flood fill function works? If you guys don't remember, it's the fill function in Paint. Are you able to recall now? It's basically a simple function which lets you color inside the borders without being messy or going outside the lines and provides a uniform look. So yes, we have to implement it by coding it. What we are given is that one pixel somewhere in this 2D array represented by SR and SC. We have to start changing colors of the neighboring pixels or elements if they have a similar value of what image of SRSC was. So for example, if we consider this green position as SRSC, we have to change it to a new color blue. We will keep doing it till we cover all the neighboring greens. In this case, it's safe to say we have only two greens. Once we hit the black or the yellow, we won't change that color to blue because now the neighboring colors are not green. If we look at this in terms of numbers, it looks something like this. The array has multiple grids. Suppose the value of SR and SC is somewhere in the middle of this 2D array and the value we are dealing with is 32, for example. Our task is to change this 32 and the neighboring 32s with whatever new color we are given. So for example, we are given the color of 25. We keep changing this color 32 till we reach some different values like 1, 0, and we can't change it. So now the new array will look like this. Okay, that was a long explanation for this problem. Let's go to the constraints to understand what type of input are we expecting. So as we know, it's a 2D array, so there will be a row and there will be a column. M is the size of the row and N is the size of the column. The size of the row and column can range from 1 to 50. The value of each element in that row or column can range from 0 to 2 raised to 16 minus 1, which is 65,635. The value of SR will always be less than the length of M, and the value of SC will always be less than the length of N. The typical questions for the graphs would be, what would my edge cases or corner cases look like? For our problem, we can have a row as small as length 1 as well as a column length which is equal to 1. This means we have only one pixel slash element and we just have to change its value. Moving to the maximum side, we can have a matrix of 50 cross 50. That doesn't look so bad. To look into how the values of colors arranged inside this matrix can affect our answer, we have to go deeper. Let's see how we approach this problem. We will use the depth first search algorithm. Depth first search is a very common algorithm to solve graph problems. So without talking a lot about it, let's look at the problem and try to understand how it works. Now, we are going to take a look at this 5 cross 9 array. We are given different numbers to specify the colors. It's a beautiful pixelated image of a lake and trees besides the lake. There are also small puddles. Now, the value of the screen row and the screen column that we will use to implement this paint function or fill function is SR is equal to 2 and SC is equal to 3. This is our head node. We now have to look for neighbors. First, let's understand what a neighbor really is. Well, they're kind of like your old video game buttons where you can go top, down, left, right, but you can't move diagonally. I'm talking about the old video games and not the new ones. So, top, down, left, right is equal to good. Any diagonal direction is a red flag. In our code, we start with the top first. We move to the top and then check if we have the same number 32. In this case, we do, so we change it. Now again, for this edge we are at, we check if its top neighbor is 32. The top neighbor is not 32, so we skip that one. We move to the right side and we check if that node is 32. It's not 32, so we skip that as well. We then check the bottom node and check if that's 32. That's not 32 as well. And in the end, we check the left one, which is also not 32. So we traverse back to the previous node from where we came. And for that node, we had already checked the top one. So now we check the right one. So I showed you how this whole traversing process works for one node, but you can basically apply the same principle that we applied previously to all the nodes we have right now, and we would get something very similar to whatever animation you are seeing on the board. The animation was really cool. So we get a grid that looks something like this. And now we can see the cherry blossoms everywhere. The important thing to note here is there are three areas that have 32 but were not considered. First one is in this bottom right corner. As you can see, they are all neighbors of one another. But no 32 in the middle from where we started is connected to it directly. So it doesn't work. There are two others that look connected or look like they are neighbors, but they are diagonally connected, so that doesn't count. And the last one is a loner, so has no 32 connected to it. Okay, that was a long explanation for this approach. Let's get straight to the code. First thing to check is if the color given to us is the same as the color in our 2D array at SR and SC position. If it is, we just return the current image that we have. We have to do this to avoid going into an infinite loop while using recursion. As we saw earlier, we are going to use the depth first search algorithm. To implement this, we are going to use recursion. As I mentioned in the approach earlier, we will try to find all elements with value 32 who are neighbors and try to change them to 25 to change their color. The function will keep calling itself till we have no more neighbors with value 25. For this color fill function, we provide the image with the 2D array we just saw, the source row and the source column, 2 and 3 in our case, which will provide the position of the pixel, the color that has to be changed in our case, which was sort of blossom pink, and 25 was the value, and the initial value at the position that we were just provided with, which was 32 in our case. In this function, our approach is to check if the neighbor at the top has the same value as the requested pixel. If it is, change the value to that color. We do this for the bottom element, the right element, and the left element. Now, the point is when we do exit the loop, I tried running just writing these conditions and got a ton of error. Well, not literally ton, but you get my point. We first check if the selected low is less than 0, which means we are out of the index. There are 4 conditions when we can go out of bounds. First, if SR or SC becomes less than 0, the next SR is greater than or equal to the length of the array. The last one is SC if it is greater than or equal to the length of the array inside the image, meaning the length of the column. We keep doing this till we find no neighbors whose value is 32. In our main function, we just return the image. Okay, if you look at the test cases, they look something like this. They're really interesting. Watch. Now, coming to the time complexity of the problem, it is dependent on the number of vertices that we have in the depth first search graph. So the graph won't be dependent on exactly the size of this 2D array, but the consecutive neighbors that we have with our target element. In our case, there were 14 vertices, so it is dependent on all of them. It will call the function recursively before calling it quits. So it will basically call through all neighboring 32s. In a scenario like this, the time complexity is going to be O of nodes plus edges, which is like vertices plus edges. So if we have a same colored background, imagine black for example, so all the values will be 0. In that case, it would take us m plus n tries to get all the pixels of the background. When I mean m plus n, I mean O of m plus n. In our case, it was 14 times 4, which was 56 tries before we got all answers. But we did not consider the constant, so it was O of m plus n. If you still think you can solve this problem in some other manner, please let me know in the comments below. There are links to, again, problems like this to solve arrays or something to do with strings or how to search things. And of course, now I'm making more things about graphs and I'll keep making more things. And you, of course, know the other thing. Like, share, subscribe, hit the bell icon, and give lots of love and feedback. I appreciate it. Thank you. Bye.